let's get started. Um, Several announcements before we start. First is final course evaluation already started. So the same rule here, 90% of you submit the evaluations and all of you will get $10 points. So that is 48 evaluations. Second is the CTF. So originally I planned is week 15 we will do the CTF, but apparently I cannot do that. I didn't know that there's a rule forbid me to use this week 15 to do any final. Okay, so we will do that at the final time, I guess. But the final time I checked is only 3 hours. So tomorrow I will talk with associate dean to say what we can do to make that longer. So anyway, it will not be the week 15, so you will have more time to prepare. There's just some rules I was not familiar with. Sorry about that. Yeah. Well, I don't know. We reserved the 3 hours, so maybe we will just do 3 hours instead of 4 hours. Tomorrow I will talk with associate dean to figure things out. Yeah. So I will update you guys tomorrow night. Okay, so for the final 2 weeks, we will talk about micro architectural level attacks. So last week we started the cache side channel attack, and today we will talk about Meltdown, which use that cache side channel attack, but itself it's not using the cache side channel attack. There's another CPU level vulnerability in that. So Meltdown and also Spectral, they are both hardware vulnerabilities affecting many CPUs, especially the Intel ones. So if you are using the new Mac, the M1, you're using an M1 CPU, I'm not sure if the experiment will work on your PC. Also, we haven't put all this to our server because it may not work anyway. So in this class, we are going to use a virtual machine developed by a professor at Syracuse, and it may work on your machine, it may not work. So those 2 vulnerabilities have been out there for 4 years. So those from the CPU companies to the system OS guys, they have been proposing many things to fix those vulnerabilities. Not directly fix those vulnerabilities, but making it harder to exploit or not possible. So technically, those vulnerabilities work on ARM CPUs, Intel CPUs, even the IBM PowerPC, but in theory, it should work. But in reality, some of the CPUs people couldn't exploit. So the Meltdown was discovered back in 2017, I believe, and it was made available early 2018. If you just search Meltdown and Spectral, you got a lot of news articles back then. It was a huge thing. One of the most important discoveries in the last decade in security. So basically, all the CPUs we have been using for 15 years are vulnerable. No one knew that. So, so several groups, I think 2-3 groups, one is from Google, the other independent researchers, they discovered those vulnerabilities independently. Then they published the papers together. So both vulnerabilities were considered catastrophic by many security analysts. So there is a website you can check later. We'll have so the Meltdown attack website that's from the authors, and also MITRE website giving a CVE for it, and also explain how serious that problem is. Anyway, today we will talk about Meltdown. Then maybe next week we talk about the Spectral. So look at the name, Meltdown. Okay, So it's basically melting down the protection we have at the CPU level between the kernel and user space. At the kernel and user space, we have a memory management unit, MMU. If you took OS class before, you know, MMU is part of the CPU. That's a CPU feature, has been there for, I don't know, 30, 40 years maybe. Our OS relies on that feature. Our security relies on that feature. Then people find out we can bypass that feature easily. So Meltdown allows attackers to read arbitrary physical memory from an unprivileged user process. So if you run a user process, a ring-free process, that process will be able to extract the kernel memory data. And in kernel, there are a lot of sensitive data. They can be extracted. They can be retrieved. Not able to write, but able to read. So this basically bypasses the protection of MMU. MMU says if you are the ring-free program, you cannot read and write the kernel memory. Because of this problem exists in the hardware, it's very difficult to fundamentally fix the problem. Very difficult, especially for existing CPUs. They're already shipped. You cannot send your CPU back to Intel to fix it. Even if you send back, probably there's no way for them to fix it, right? So, so most approaches are still software level and system level remedies try to make this more difficult to exploit. Some of them even very difficult to fix for new CPUs because you need to sacrifice the performance. Those problems exist because the CPU designers try to make CPU execute faster and faster, taking advantage of all kinds of optimizations. But those optimizations will leave some doors for us to hack. So the Meltdown attack is quite complicated. So a professor from Syracuse, he actually had designed some experiments, were designed to break Meltdown into smaller steps. So I'm going to follow what he has there, and in the homework, you are going to follow those experiments. We already saw 2 of those experiments actually last week. By the way, in the final exam, the final CTF, there will be no challenges on Meltdown spectral or cache because they are probabilistic, may not work. But you still need to do the homework. Some of you may not be able to run them successfully because of your machine. You just need to faithfully record what happens on your machine. Okay. Most of you, I think, you will be able to get the results. So Meltdown, the root cause of this vulnerability is optimization feature called out of order instruction execution. So this is another CPU optimization introduced decades ago to make your CPU run faster. And because of this optimization, the CPU will leak data and using the cache side channel to leak the data actually. The problem is not fixed, but Linux, Windows, they have some system level patches to fix the problem, to remedy the problem, something called the kernel page table isolation. We'll talk about this later. Okay, so first of all, we talk about what is out of order execution. So some of you may remember this from your computer architecture class, I guess. So let's say, so to understand what is out of order, let's first understand what is in order execution, what is in order pipeline. We have a, let's say we have a CPU here. The CPU has a five-stage pipeline. So they are F, D, E, R, W. So F is fetch. So to fetch the instruction from the main memory, because your instructions are stored on the main memory. The CPU has to retrieve that. Now after CPU retrieve that, the CPU needs to understand what instruction that is. So that is a decode. That is a decode phase. So that's F and D. So after the CPU understand what instruction is it will execute that. So execute that may take multiple cycles. Let's say one square there is one CPU cycle. Let's say an integer and instruction will only take one execution cycle. An integer multiply may take 4 CPU cycles, or a float pointer multiply will take 8 cycles. And there are other instructions may take even longer cycles. So after that, to execute that instruction, the CPU will also need to read the data. So that is R cycle to read data. Also, there is a W1 to write back data to register and also memory. So for instructions, you can imagine they are sequential, they are one by one. So some of the instructions are depending on previous instructions, not always, but some of them are. So the problem here is from a CPU designer's point of view, the problem is if there is a true data dependency between two instructions, the instruction 2 depends on the instruction 1. The result, the instruction 2 has to wait until instruction 1 finish execution, right? Because it depends on data. But if they do not depend on data, then they can actually execute at the same time. So let's look at one example, basically 2 examples here. So we have 2 examples. Those are two code snippets, assembly. Each of them is 5 instructions. And let's take a look what they are in common. The left-hand side one, we have 5 instructions. The first one is we multiply the value in register 1, R1, and R2, and we put the data in R3. So I, MI, and UI, that's MUL, that's basically integer multiplication. Then the second instruction we have is and the value of R1 to R3, then put the value back in R3. So you can see the second instruction depends on the first instruction, right? The second instruction, we needed the value of R3. So there is no way we can execute the second instruction first, then the first instruction, right? However, if we look at the third instruction, the third instruction is we add R6 and R7 to R1. That instruction technically is not conflicting with the second or the first instruction. We're reading from R6, R7, writing it back to R1. So of course, we cannot write the value back to R1 before the second instruction returns. Then the fourth instruction will multiply R6 to R8, then put the value in R5. So look at the third instructions and the fourth instruction. They are totally independent, right? They are using different registers. They're not relying on each other. So if we swap the order of those two, so technically the program still is equivalent, doesn't really matter. So technically we can execute one of the instructions earlier than the next instruction. Then the third instruction, the last instruction, the same thing. Okay, so you see the problem here is, let's say we only have in order execution. We only execute the instructions one by one. So the second instruction, we have to wait for the first instruction. The third instruction has to wait for the second one. The fourth one has to wait for the third one. Then if the first instruction is slow, then everything slows down. The code at the right-hand side has the same issue. Then that's why those smart engineers, CPU engineers, they come up with the idea called out of order execution. I'm not really a computer architecture guy. I don't design CPUs, but there are a lot of optimizations at the CPU level to make things faster. And to me, as a security guy, I think a lot of those optimizations will leave vulnerabilities. So the out of order execution is also called dynamic instruction scheduling. The idea is very simple. So we move the dependent instructions out of the way of the independent ones. Then we can execute those independent ones first. We do not have to block the independent instructions for the dependent instructions. So to do that, we need to monitor the source values of each instruction. When they are available, we're going to execute them. When it's done, we put them the results back to the registers or memory. So let's see two more concrete examples using those 5 instructions we just saw. The first, the in order dispatch is on the top. The out of order dispatch is on the bottom. So how many of you are familiar with this kind of graph? What is this graph called? Is it called in computer architecture class? What is this graph called? Dispatch graph? I don't remember anyway. Okay. So let's say pipeline graph. Yeah, something like that. Yeah. So you can say for, let's say, the in order one, we have 5 instructions. And the pipeline graph, we have 5 rows. So each row maps to 1 instruction. Then there are so many different columns. And that column, each column means 1 CPU cycle. For example, at the very first CPU cycle, we only have the F there. Means F on the first row. This means the fetching unit is fetching the first instruction from the memory. The second column, we have D and F, which means the decoding unit is decoding the first instruction, and the fetching unit is fetching the second instruction. So this CPU, we only have 1 fetch unit, 1 decoding unit, 1 readback, 1 read, 1 W, but we have at least we could have multiple execution units. So if you look at this, you can say at each column there is only 1 F there, 1 D there, actually only 1 E there. So here actually 1 E. We have 2 execution units there. So for the first instruction, the integer multiply, what happens is we fetch, we decode, we need 4 cycles on that execution unit, then we read, then we write. For the second instruction, what happens is we fetch, we decode, then because we needed the result, the second instruction, we needed the value of R3. So we have to wait there. We cannot execute, okay? So we need to wait until the first instruction finish execution, then we can execute. Even though this instruction is very fast, it only takes 1 cycle, it will get blocked there for 3 cycles. Then because the second one is blocked, the third one will also be blocked. And you can see in total, to execute those 5 instructions, we need, this is 5, 5, we need 16 cycles to do that. At the end, from here to here, that's 16 cycles, we finish executing those 5 instructions. But we already know that the last 3 instructions has nothing to do with the first 2 instructions. So to speed things up, what we can do using the out of order feature is, first, the first instruction executes, it will take that 8 cycles. It's not wasting any CPU cycle there. Then the second instruction executes, it do F and D. and it has to wait for the result of the first instruction, right? So it waits there. So the second instruction will not be executed actually. The execution unit is not working on the second instruction. However, the third instruction has nothing to do with the first two instructions. After fetch and decode, it will execute. So the third instruction actually executes before the second instruction. See that? So the CPU is not faithfully executing the commands. It relies on some dependency and try to speed things up. And even the fourth instruction will execute before the second instruction. You can see that this CPU cycle, the fourth instruction starts execution. However, only one cycle later, the second instruction executes, even the one this one takes time. And you can see that for this CPU, obviously we have two execution units, so that's why it's possible. Okay, so use this out of order execution approach. We can save 4 CPU cycles from 16 to 12. That's 25% performance upgrade. Okay, so you can see those simple optimizations without making your CPU bigger, without adding more transistors to your CPU, without making your CPU more expensive, it can make your CPU run faster. That's why those features are very important in real life. However, the problem is they open doors for all kinds of attacks. But unfortunately, it's only discovered decades after the optimization was introduced. So let's see how the meltdown attack works. In meltdown, our scenario is we have a, let's say, a modern operating system like Linux, and this is the address space of a Linux process. And the Linux process will have its user memory, and actually they will also map the kernel memory for performance reasons, but it will not be able to access that. You write a program, in that program's address space, you can see the kernel is mapped, but you cannot access that. When you access, the MMU will say you don't have a permission, it will kill your process. Let's say there are some secrets, maybe secret data in the kernel, and we're just running a program here and we want to steal that secret data from the kernel, which MMU do not allow you to do. What we do is, in the first step, the user process will just try to read 1 byte from that secret. So what will happen? The MMU will stop you, right? So your program probably will crash. It doesn't have to crash actually. What the MMU, the OS does is it will throw an exception. And if you do not handle that exception, the OS will handle it and the OS will crash your program. If you handle it, if your program explicitly handle it, you don't have to crash. I will show you code later. Anyway, you try to access some secret, but you will not be able to. You'll not be able to do that. However, what happens is utilizing that out of order execution, you can make that access happen before the CPU realize you don't have the permission to read that data. The CPU will read that data from the kernel first. At the same time, the CPU will check whether your program has the permission to read the data. It happens at the same time, but reading the data is faster than the CPU checking if you have the permission to do that. So you will be successfully reading the data, then very soon the CPU will realize you don't have the permission to do that. So the CPU will revert that result. And the interesting thing is, even if the CPU reverts the result, it will leave that in the cache. You will not be able to read that data into a register or memory, but it will leave in the cache. And then you use cache side channel attack to infer what that is. That's the basic idea of this. Let's say one concrete example. Like I said, this example is quite complicated. The most complicated example we have seen so far in this class. There are kernel modules, there are username applications, and there are exception handling code. Let's start with the kernel part. So the kernel part is not the code, is not the attacker. That's a secret. Okay. Technically, you can steal information from any kernel memory, but let's say we have some secrets there planted in the kernel, and we want to steal that. So this piece of code is actually a kernel module, or you can call it a Linux driver. If you develop Linux kernel, most likely you develop some Linux driver. It's called driver because 20 years ago it's basically device drivers. But device drivers are basically kernel modules. Okay? They don't have to map to any physical device. That's why you can see at the end of the program. So the first thing you notice is this is a full program. The program doesn't have a main function, right? That's a kernel module. It doesn't have a main function. Instead, you first declare the entry point and the exit point of the kernel module using the module init, module exit function. Maybe the macro. I'm not sure if they're functional macro. Anyway, so you define that for your module, the entry point is test proc init, and the exit is test proc cleanup. So you use Linux command install module to install your module. The init function, this function will be called. When you remove this module, this function will be called. Right? So that is how kernel module works. Then at the init function, let's say it's here. Let's see what it does. It will first print out the address of our secret. That's what we want to steal. So here is one thing. If you want to steal some data from the kernel, you need to know its address. That's one of the requirements of Meltdown. You need to know where is the thing you want to steal. And you notice that we're using the function print k here, okay? It's not printf. Remember, printf is a C library function. So when you write a program, it links with the C library, and they are all userland code. Here, everything runs in the kernel. The kernel doesn't have a C library for you to use. So there is no printf to use. Instead, the kernel provides a function printk, print of kernel. It's like almost the same. I think it's actually the same prototype as printf. So this is how you print out the address of the secret. And the secret here is just a global variable. We have 8 bytes of secret, just a safe lamp. That's the professor who developed this lamp. So we print out the address of that. Then we create, so we use vmalloc to create some kernel memory, 8 bytes of kernel memory. So this is different from malloc, right? Malloc is also a C library thing. That is a dynamic memory management in user space. Here we're all inside the kernel. Then we get some buffer, and the buffer we call it a secret buffer. And this buffer is also inside the kernel. Then we create an entry in the file system, the proc file system. If you use Linux, you know the proc file system, you can retrieve a lot of information of the kernel. So we just create a file under that pseudo file system, we call it a secret data. And for this entry, we will be able to open it. We will be able to read it, and we have a seek release, you can say. So those are other system call names. The open is a system call, read is a system call. So if you use open this file name, you will be open this file. But what actually happens is when you do that open at the usernet at the kernel level, is this function, the test proc open, this function will be called. And what this function does is this one will just open a file. Okay, not much to do. And the read one is not going to give you back the secret. The read one will only move the secret from its own global variable to another kernel heap global variable. We're moving data from kernel to kernel. We're not moving data from the kernel to usernet. So if you do a read, you're not going to get the result. Okay, that should be clear. So now, so basically this program only gives us the address of the secret. And also if you do a read, you make sure that secret is actually used. The purpose to do that is to bring that back into the cache. That's the real purpose. Okay, everything makes sense so far? Good. That's a kernel module. Now let's say we already know the address of that secret. For example, that's FB61 that is the address of that secret. And this is our username code. The username code will have a pointer pointing to that address. Then we just dereference that. If this works, we should be able to get the character S, right? We're only getting one character, and that should be the S. However, it will not work. It will. So this is a username application. There is a printf. So we prove that it's a username application. It will never reach here because this instruction here, this statement here, will generate a segment fault. You will not be able to retrieve that byte, that secret byte. So, like I said, that even though there is a segment fault, so far our programs will never handle segment faults. You can actually, so when segment fault happens, the OS will just crash your program, remove your process from the system. We can actually stop that. We can capture the segment fault. We tell the OS when there is a segment fault happens, I want to handle it. I don't want you to directly crash me. That is a feature allowed in Linux. So we're changing this piece of code to this. So when segment fault happens, we're not going to crash. Instead, we will stay alive and try to access the same location again. Here we're using a feature signal jump and the signal long jump. So how many of you used the set jump and long jump before when you're programming in C? That's kind of like C's exception handling mechanism. C doesn't have a built-in exception handling mechanism like C++ or Java. That's why it has something like this. So this one is set jump. It's similar to set jump. It's just we are handling signals. Signal is also a feature in the Linux or Unix system. Let's say what we do here. We have the address of that secret, that uppercase S. Then we set the program, we'll set a signal handler. We are going to handle the signal segment, which is a segment fault. When segment fault happens, you do not crash my program. Instead, you call my function catch segv here. So by doing this, the OS will not crash your program. Instead, it will call the function you give, which is catch segv. Okay. Then I will set kind of like a set restore point. I will set a restore point at here, the if. In this, if the restore point is set successfully, what I will do is I will access that kernel address. And when I access this the first time, the program will crash. The kernel will send the program seek segment fault. Because of that, after this one, I'm not going to execute the printf. Instead, I'm going to execute the catch segment function, which will have a long jump to the original restore point. Okay, so this is quite complicated stuff in C. So anyway, this is a magic, but this function set a magical restore point. When bad things happens, we jump back here. The program keep executing from here. So we'll keep accessing this secret data. So if this setup was not successful, we will print out violation and the program will exit. So this is a exception handling part. Okay, so the reason that, like I said, the reason that we may steal the data is because when we do this memory dereference, we try to read that kernel location for the secret. The CPU actually does two things at the same time. One is the CPU will check the MMU, which has a big table, page table in the memory, to check if your instruction has the permission to access the data. And this step will be quite slow because it has to check the page table, which is in the memory. At the same time, the CPU wants to speed up things. So it uses out of order execution to actually bring the data from the kernel to the register and keep execution to speed up things. So when this happens, so your code keeps execution, then the CPU check with the MMU and feels that you actually do not have the permission to do that. So the CPU will quickly stop the out of order execution, roll back to where it was before. So the out of order execution results should be discarded. However, when they roll back, they only roll back register. They do not roll back the cache. That's a problem. Okay. So that's why it leaves some information in the cache. Okay, so now we put things together. This is how we are going to steal data, the secret, from the very first program. This one. This is a kernel program. We're going to steal data, the secret from here. So this is our user NAND program. This is just a user NAND program. It's going to steal the kernel data. So what we do is we have a main function. In the main function, we will catch the segment fault error. Then after that, we will flush the side channel. We're going to use flush and reload. We're going to flush the side channel. So we know that nothing important is in the cache. Then we're going to call the meltdown function. And let's take a look at the meltdown function. The meltdown function actually is simple. We have a local variable kernel data. Then we just dereference that kernel address. That's it. This will not be successful, right? This should not be successful and will not be successful. But the problem is, after that, there is another instruction, or C level is a statement. In this statement, we are going to use the kernel data. We're going to bring that kernel data to the cache. Remember that a flash reload we used before? We used this one to, here we use the 207, remember? So we can say if we can bring some data into the cache, it will be much faster. So here we're using that, right? So if you look at this piece of code, this statement should not be successful. This statement should not be successful. So this one should never be executed. But actually, the CPU will execute this one because of the out of order execution. And what happens is when we execute this one, this value, the location of that value, will be brought into cache, right? Now after that we brought into cache, the kernel realizes you don't have permission to do that, then it kills this. So this array, let's say this is an array, so this is the main memory. We're trying to +1 to its own data. We'll add 1 to that. So that will not happen. After this, the data out of that array will not be changed. It will not add 1. However, it will already, that will be brought into cache. So after that, we do a reload attack. So flash and reload. So reload, we're going to retrieve all of them together, all of them one by one, and try to measure the time. Then we will find out that item, the kernel data, in this case is S, it will be faster because it has been brought into cache. So that is how we steal this from the kernel. Make sense so far? In this specific example, the kernel data is a character S, but we don't know that, right? That's something we want to steal. Which one executed before? This one? So this one will not execute before this one. No, this one, not before. This one executes before the checking on this one, the check result, the permission check comes back. Because there's still a data dependency. This one depends on this one. So you cannot execute this first, then this one. No. Yeah. But you can say this one, the problem here is you're doing two things. The one is you're moving the kernel data from the kernel memory to this local variable. The local variable is a user programs in your user program memory, right? On your stack. The second thing is you need to check, the CPU need to check if you have the permission to read this data. And the checking if you have the permission to read that data takes longer time. That's why it's doing both things at the same time. It's checking if I have the permission and also moving the data. After you move the data, what happens is then it will keep execution this one. Then that data will be used to bring something into the cache. Then after that, maybe after executing this instruction, the CPU realize you don't have permission, so I need to roll back everything. The array, I will roll back. So previously I add 1 there, I need to -1. And the kernel data might probably place something there. I need to roll back. It should not have that. However, it will not roll back the cache. That's a problem. you are technically you are not directly forwarding the data into the cache. Look at here, right? You're actually using that data as an index to brought whatever in that you have a huge array, brought a huge arrays data using that secret of the index into the cache. And that operation itself doesn't have any memory violation. Yeah. Yeah, that's basically how Meltdown works. Well, it's very complicated. It took people several decades to find out the problem exists. Since then, there have been many defense. One of the useful defense, not a direct one to fix this because it's a CPU problem, optimization problem. Well, let's say the CPU can disable out of order execution. Then we don't have the problem, but the CPU will be much slower. Another defense is to use the system level is called the kernel page table isolation. Basically, the idea is previously a process were mapped to the kernel memory for performance reasons. Now we do not map it. As long as you do not map it, when you do this, you will still get a segment fault, right? Let's say this address is a kernel memory address. When you access it now, you get segment fault. But there is something at the address, so the CPU keep execution. If you do not map that, there is nothing at the address. You still get a segment fault, but that will not be brought into the cache. Okay. But because of that, there will be some performance issues because mapping that is to make system faster. And also some parts of the kernel memory cannot have to be mapped, except for example, the exception handling part, they have to be mapped. So if you remove the kernel mapping, you are still not removing everything. There are some small things left there, but they probably not very serious anymore. Okay, you can see this is a kernel patch quickly released by Linux. It doesn't address the root cause of the problem, just to prevent practical attacks. Also, another thing is the kernel level address space layout randomization. So you can see the requirement here is you need to know the secret address. We can make that a little bit harder. We randomize the kernel. However, kernel level address, so program level address space layout randomization happens every time you launch a program. If the program keep running there like a web server, it keeps running there for days and it forks itself, then it's not safe. The kernel level address layout randomization will only happen when you reboot the kernel. And for modern computers, how often you reboot the kernel? Not very often, right? So still, it's not that secure. Also, the entropy is not that big. Okay, so for the rest of the class, I will ask you to do this attack by yourself. You will follow this link. I already put this slides online. You will follow this link. Try to the professor break it down into 7 tasks. Those first two tasks we already did last class on our server, but you can do this on his virtual machine. Like I said, it may not work on your computer. We just need to figure out if it works. I don't know.